Oh, I know what it is.
Smallest range.
This right here, between the red is 68. Between the green that is 95. And between the blue this would be 99.7%. Okay. So in this problem for B, the central 95 will be between 68 through 132. That's 1 standard deviation below, excuse me, 2 standard deviations below, and 2 standard deviations above. See, 100, you see our normal model, what we're doing, this is the normal model, where the center is at 100 and the standard deviation is 16. 2 standard deviations above is this, 2 standard deviations below is that. The rule says this area between these two segments of my hands here, the curve on the top and this on the bottom is 95%. 95% of individuals in this model will have scores between that 68 and 132. All right, for C, the question is about what percentage of people should have IQs above 116. Okay, so basically what we want to do is we want to find this area over here. And let me sketch that. So we're asking what is that area right here? Same normal model. I just abbreviated away the rest of the details. Well, this is how it works. First of all, this curve is symmetric. If you pick it up and flip it over relative to the center, it looks identical. So half of the area is to the left of 100, half is to the right. So below 100 is 50%, above 100 is 50%. Now let's take a look at 116. Now the rule we were given was that between 1 standard deviation above, 1 standard deviation below, which are these two numbers, of the center, we have 68% of the area. What's the area between 100 and 116? Well, by symmetry, it's half of that.
34%.
So 34%. So now, this right here is 50%. This is 34%. What's the area to the right? It's 100 minus 50 plus 34. So, I'm just using some geometry here. It's 100%, which is the total area. And I want to subtract the sum of 50% and basically 68% over 2. So this is 100% minus, this would be 34, so this is going to be 84%. And I guess that's equal to 16%. Did that right? 16% of people using this model should have scores of 116 and above. I'm making use of some very basic geometry. First of all, there's symmetry. the total area underneath any normal model is 1 or 100%, equivalently 100%. So half the area is to the left, half is to the right. Half of 100% is 50%. Now, if between 84 and 86 is 68%, then between 100 and 116 is half of that, or 34%. So if I want this, all I have to do is take 100% and subtract from it these portions here. That's what I did in this case. Okay. D, it says about what percent of people should have IQ scores between 68 and 84. Whoops. Well, basically what I want to do is the following. I want to find this area right here. So let me just kind of quickly sketch that. So the question is, what's that area there? Well, this is what we do. What's the total area between 68 and 132 is 95, so between 68 and 100 would be half of that. So between these two, or this portion here, would be half of that. So that's going to be, what, 47.5%? Now, so that's this area right here. What was this area here? It's the same as this. This area here we figured out to be 34. Okay, so this is 34. This right here is 47.5. So I take the difference to find this. So the red, if you will, is 95% over, whoops, about 68. So this is 68% over 2. The green, which goes from, say, here to the same line here, the green is 95% over 2. So that's going to be 47.5%. This would be 34%. So this right here is 47.5. This right here is 34. So the purple is 47.5% minus this portion, which is 34%. And that's equal to then 13.5%. Okay? Now in this analysis, all that we're doing is we're using that 68, 95, 99.7 rule. We're going to find a more sophisticated rule of addressing these questions momentarily. All right, now, in part E it says about what percent of people should have IQ scores above 132. So looking over here, we're basically asking how much area do we have to the right of 132? Well, there are a couple ways of thinking about this. Between 68 and 132, which are symmetric about the center, we have 95%. So on the two tails, each tail we have 5% over 2. Okay? So, let me So above 100, let's see, this is E. This is 100, 132. So we're asking, what is this area here? Well, I claim the following. Basically, what we want is 100% minus 95% over 2. And that's going to be equal to 2.5%. In other words, if I want the area to the right of 132, I want this. Well, between 68 and 132, which are symmetric distances about 100, we have 95. Therefore, the two wings, when combined together, has to be 5%, and it has to be divided in half. So that would be 2.5%. Okay.
Can you go over part B again? I didn't use the current.
Part B?
I'm sorry, D.
D. Okay.
I finished that E and C, but
Okay, so we're asking for how many people will score between 68 and 84? Okay, let's go back to this diagram here. Remember, the center is at 100. And between 68 and 132, that region is centered about 100. And we're given the rule that that's 95%. So halfway between, or half of that, that is between 68 and 100, I should have half of 95. So that's where I have the 95 over 2. That represents this area right here. Now, I already figured out in this problem, one of these problems, that this area right here was 68 over 2, or 34. See, between 84 and 116, which are symmetric about 100, this area here is 68. Therefore, the area from 84 to 100 is half of that. So that's 34. So this right here is 34, and all of this is 47.5. Then this would be all of this with that removed. Okay? This is how you want to think about the notion of areas. We're going to get a slightly more sophisticated, because what we're going to do is we're going to be using what's called the standard normal table, and we'll get to that momentarily. Okay. Let's jump ahead to number 38, which is again based on the same normal model. The center is at 100 and the standard deviation is 16. So let's let me write that down over here. And we'll start over on the left. Okay, again we have the same model, normal model, and let me just do a quick sketch. All right, now in part A, it says how many people are going to have a score of over 80. So 80 is on the left here. All right, there. And basically what we want to do is we want to figure out this area right here. Now, unfortunately, the 80 does not fall on one of those nice boundaries, which is a multiple, if you will, of the standard deviation. So this is the way we deal with that. We compute a z-score. And this is how we do it. We take the value that's going to be of interest, in this case it's 80, and we subtract from it the value of mu that's appropriate to the model we're using, divided by the standard deviation sigma. So in this case, it's going to be 80 minus 100 over 16, and that's going to be a negative 20 over 16. And if you whip out your calculator, that will turn out to be a negative 1.25. Now, the next thing I'm going to do is I'm going to sketch what we call the standard normal model or distribution, where the mu is equal to 0 and sigma is equal to 1. This is again a bell-shaped curve where the peak is above 0, and this horizontal line is often represented, the values there are represented by z, in the same way that we might represent values along this horizontal axis by the letter x. In fact, that's what I've done here. In this formula here, I took the value of x that was of interest, namely 80. This was 80. And I converted it into what we call a z-value or z-score using this formula. I end up with negative 1.25. And what I'm going to do is I'm going to identify negative 1.25 on this horizontal line. On number lines, numbers to the left are less than numbers to the right, and negative numbers are to the left of 0. Okay? So the equivalent question I claim is the following. What is this area here? The question was originally posed in terms of this normal model with that specific value of 80, I claim is equivalent to answering the question, what is this area underneath the standard normal model? That's a theorem in math. We're going to be using that repeatedly. Okay, how do we figure that out? Well, what we do is we refer to a table in the back of our book, all right, called the standard normal distribution or standard normal model. And what I'm going to do is I have a copy of that. We'll bring it up online. This is basically a copy of what you have in the back of your book. And if you look at page, in your text, it's on A64. If you were one of the lucky ones who was able to buy an instructor's model or instructor's version, this would be A110. But for the PCC edition, there should be an appendix A64. And it says Table Z. Table Z is the standard normal model. It says areas under the areas under the standard normal curve. Okay, now what we need to do is we need to learn how to interpret this table, which will help us address this question right here. And I suppose it will be helpful if I bring this down here. Now what I want to do is these numbers, which are on the interior of this table, what I want to do is I want to find the number here, all right, which is as close as possible to a negative 1.25. Okay? So let's make this a little bit smaller. And let's see, we'll even make it a little bit smaller. Okay. Now in your table, on the first page of that table, on the right-hand side, you'll see a column of negative numbers. What I'm looking for, and let me replicate that so we can. So I have a standard normal model where the peak is above 0, and I have the z value of a negative 1.25. And I'm asking, let's see, I'm asked for this area right here. That's what we were asked for. Now what I need to do is I need to find the entry on the interior here associated with a negative 1.25. Negative 1.25 can be thought of as a negative 1.2 plus a negative 0.05. Now, so I'm going to use the row which has at the left negative 1.2, and I'm going to move across here until I'm underneath a column where it has 0.05. There's not a negative sign there, but that's understood. So the entry 0.1056, what is the meaning of that number? That actually gives us the area that's to the left. This area right here, which is what the table gives us, .10, is it 96 or 56? 56. Which would be the same as the percentage, 10.56%. Okay, now, if I know this area here, what is the area to the right of it? It's 100% minus that. So this, right here, is 100% minus 10.56%. And that's going to be 89.44%, which is approximately 89%. This here, or this is this area here, which I claim is the same as this area here because of the equivalence that I said follows from a theorem in math. So this is then approximately, I'm just going to put down the approximate, it's about 89%. About 89% of people will have a score of 80 or above. Or we could even round it up and say 90%. All models, the models are exact, but no model ever fits real data exactly. So we might, rather than putting down 89%, we might say, look, it's probably about 90%. Rather than 89% gives a little, maybe a little too much precision. About 90% of the people in this hypothetical example would give a score of 80 or above. What's the humor?
Well, it's just the approximateness is so different than.
And you thought we were giving exact answers in that. This is probably a shock to people in math because, and actually if you do things in, I mean if you've had lab courses chemistry courses, biology, and you're working with numbers, I mean, you're always using with approximations, all right? And typically in math, there's only one right answer, and it's exactly this. But when we get into the realms of statistics, that's when we start being, it's a kind of different type of math. And there are a lot of people that can teach math that don't want to teach statistics for exactly that reason. It's a little too wishy-washy. But this is the real world. Okay. So everyone understand how I got this answer here? What I did is I converted it into a z-value. I took the 80, used the parameters 116, and I converted it into a z-value. The z-value is this. I then used the table, the standard normal table, and I found this area by finding the intersection of a negative 1.2 on the right and 0.05 on the top. That represents the area to the left. To get the area to the right, I took that from 100%. Yes?
How do we know that for that one it's 80 is the value, that we're using it on that side, it's the 1.25. How do we know what to go to in the back of the book? You know what I mean? If that was our question, our homework.
Well, you always compute a z-value.
Oh.
Okay. Once you compute the z-value, the reason we use the letter z is that it's supposed to trigger like a Pavlovian response. Aha! The standard normal distribution. Back of the book. Anyone know what the Pavlovian response is? Yeah, I mean, this is, if you took psychology, there was a Russian psychologist who trained dogs. Actually, the experiments are more gruesome than I'm going to describe. I didn't realize this until recently, but they trained dogs so that anytime they heard a bell, they knew they were going to get fed and they would start to salivate. So you see the word Z and you start to salivate. I don't need to salivate, I just go to the table, the standard normal table. Okay? I want a Pavlovian response, but not the salvation part. Just go back to the back of the table. All right. All right, so that was problem or part, let's see, that was part A. Part B, under 90. Okay, so let's, so in part B, so under 90. Well, what I'm going to do is I'm going to sketch, again, a quick sketch for my normal model. And the reason I do this is primarily just to kind of help me understand what we're doing. So 90 is about, this is 100, this is 90. So under 90, basically I want to find this area right here. What's the first thing we do? We compute a z-value. In order to compute a z-value, I need to know what mu is, sigma is, and the value that is of interest. I know that in this case. I've been told that mu is 100, sigma is equal to 16, and x is equal to 90. So I have 90 minus 100 over 16. Now let's see, that turns out to be a negative point. See, that's 10 over 16, so that's 5 over 8. That's negative 6.25. I think that's right. Okay, now, Uh-oh, there's a problem with this. We'll see what it is in a moment. We're going to use the table again. And now what I want to do is I want to find the entry associated with the negative 0.625. Let me write it over here. So Z, again, is equal to a negative 0.625. So what I'm going to do is I'm going to, well, let's see. It's actually further down in the table. All right, negative 6.2. All right, here's a negative 0.6. So I move to the left until I'm underneath what is at the top, 0.02. I actually want to choose halfway between these two values. You see, this is associated with a negative 0.62. This is associated with a negative 6.3. And I actually want negative 6.25, halfway between these two entries. So one way of doing that would be to take the average. So via the table, area to the left is, and let's see, that's going to be 0.2676 plus 0.2643 all divided by 2. And I come up with an answer that this is equal to 0.26595 and so forth. Way too much precision. So, the area to the left of negative 0.625 underneath the standard normal curve model is about 0.26595. That's the same as this area right here. So what I'm going to do is, let's round that. And I guess we'll round that. We could either say that's 26.6% or 27%. Now you will note this number here is not so different from this or from this. If I were to round this to the 10th position, this would be 0.26 or 26%. This would be 27%. And actually, either answer would be acceptable as far as I'm concerned. It's not as though we're looking at the difference between night and day. Typically, today, we don't use tables to figure out these percentages anyway. Okay, there's actually a way in Excel. I don't think I'll get to that today, but you can do all this work in Excel and save yourself at least looking at the table. But the table is a nice kind of visual representation of all the information at once. And so that's why I use it. Again, we'll come back to this probably next week, and I'll show you how to use Excel to get these values. And your calculators, I think, if you have a TI TI 83 or 84 or 89, it will do the same thing. Okay, so what we're saying here basically is the following. About 27% of all people will have a score of under 90%. Or not of under 90, not 90%, 90. The score is 90. Okay, now, in C, it says between 112 and 132. Okay, so let's address that question. And I think what we'll do, I'll make use of the board over here so that we don't have to erase all of this. So in part C, it's between 112 and 132. So if I sketch my model, the peak, of course, will be at 100. Now, 112 is about right here, and then 132 is right there. That's the area I want to find. There are actually a couple ways of doing this. The way I'm going to do it is as follows. I'm going to compute two z values, one associated with 132 and one with 112. So let's do for the 132, that's going to be 132 minus 100, all divided by 16, and that's equal to 2. 132 is actually 2 standard deviations above 100. The next value, z, would be 112 minus 100 over 16. And that's going to be 12 over 16, and that's going to be 0.75. So this is what is being asked. This is my standard normal model. The peak is above 0. 0.75 is about right there. 2 is about right there. And we're asking for this area right here. Again, because of a theorem in math, this area here is the same as that area there. This is actually an idea from calculus. Okay, now, what we need to do now is we need to look up in the table entries associated with 0.75 and an entry associated with 2.0. The entry associated with 2.0 will be all the area to the left. When we look up the entry for 0.75, it will be this area to the left of that. And so I'll take the larger area minus the smaller area to find this right here. So this, let's figure out what that is. Now the standard normal table actually has 2 pages. The first page is associated with negative z values, and the next page is associated with positive values. So I want to find in this table the entry associated with z equal to 2. Well, 2.0, and then if I look at the top, you have 0, 0 at the top. So this is the entry, the area to the left of 2.00 is 0.9772. Now, what's the area to the left of 0.75? Well, I go to the row which has at the left the 0.7, and I move across here until I am underneath the entry which has at the top 0.05, and I have 0.7734. And if I take this difference, let's see, this is going to be the 8, and then it'll be 3, and it'll be 2, 0, or about basically 20%. About 20% of all individuals will score between 112 and 132 on an IQ test, this IQ test. Okay. Let's take a look at number 40. In number 40, instead we're going to look for scores associated with various percentages. We've kind of reversed the process. Here we wanted to know what percentages were in various ranges of scores. Now we're going to do a kind of a reverse problem in the sense that we're going to ask, well, what percentage, if we want to find the score for which 5% are above and so forth, how do we do that? How do we figure that number out? So the model is the same, and for part A, let me sketch what we're trying to do here. So this is my normal model. Peak is above 100. And I'm looking for a value of X, or a score, if you will, where this is 5%. And the question is, what is that score? All right, now what we need to do is we need to use the table in the reverse sense. So, this is how we go about doing this. I'm going to look at my standard normal model and ask the question, for what z value is this 5%? This is how we go about doing it. If the area to the right is to be 5%, then the area to the left has to be 95%, because the total area is 100%. Now, so what I want to do is I want to look in this part here on the interior, find the number that's as close as possible to 0.95, and then figure out the corresponding value of z. So I look at this table, and let's see, aha! I have two entries. One entry is 0.9495, and the other entry is 0.9505. Two entries in my table that are very close to 95%. So again, it's, let's see, these two values right here. What is the z value associated with 0.9495? Well, if I look to the left, it's 1.6. And then if I look above that, it's 0.04. So I have two z values, 1.64. That's associated with that value. This value here is 1.65. So this is associated with, let me write it down, 0.9495, and this is associated with 0.9505. Halfway between those is exactly what I want. I want 0.95. 0.95 is 95%. So what Z value do I use? This one or that one? Well, how about averaging? That's a good way. Get halfway between those two, and that will be a good estimate of halfway between these two numbers here. And what's halfway between this number and that number? Yeah, 1.645. So now, so the Z value I want is 1.645. To the right of that value is 5% of my area underneath my standard model. Now, how does that help? Well, what we do is we use the equivalent formula, which says that X is equal to mu plus Z times sigma. If you take that other equation, Z is equal to X minus mu over sigma, and solve for X, you get this equation right here. So the corresponding value of X would be the value of mu, which is 100. The value of Z is 1.645. And I multiply that times the value of sigma, which is 16. If you do the calculations, this turns out to be 126.32. And so what I can do is I can approximate that call 126. And this is what I can say. About 5% of people will have scores of 126 or larger. Okay. Part B says the lowest 30%. All right, so on to B, I want the lowest 30%. So again, sketching my normal model, I'm looking for an entry here, a value for which this is 30%. How do I do that? Well, we refer to the standard normal model. And I find the value of Z for which this area here is 30%. So I use the table in the reverse sense. Now, on the first page of the standard normal table, I have areas based on negative Z values. On the second page, I have areas based on a positive Z value. What page do you think I want to use? Yeah, you want to use the first page because the first page will have basically areas of 1/2 or less. And I'm looking for 30%. Okay? So what I'm going to do is we'll make this a little smaller, so just in case. and we'll go to the first page. I want to find an entry here that is close to 30%. And if we look in here, aha, let's see. Okay, here we go. This is actually 30.15%, and this is 29.81%. This is actually a little closer here. So what I'll do is I'll use the z value associated with this entry. What z value is that? Negative 0.5. And if I look at the top, I'll see that's associated with 0.02. So this entry is associated with a negative 0.52. So my z value in this case is a negative 0.52. How do I figure out the corresponding value? Let's see, where did I? Oh, here. How do I figure out this value here, the value associated with the IQ test? Well, basically I do the same thing. I use this formula here. Mu is 100. Z is a negative 0.52. That's 16. And if I do the calculations on that, well, let's see, it's going to be about 94. How do I know that? That's about 1/2. 1/2 of 16 is 8. 100 minus 8, no, it's 92, sorry. But we'll give it an exact answer. So this is 91.68, which is approximately equal to 92. So about 30% of people will score 90 or below in this standardized test. All right. Finally, let's take a look at C. It says the middle 80%. So this is what we're looking for. The middle 80% means two values, an equal distance about 100, so that this here, this area here, is 80%. So this, what we want to know is what is the left and the right hand side, and these two numbers have to be the same distance from 100. That's what we mean by center. Okay, so this is the normal model centered at 100 standard deviation of 16. First thing is we do is we're going to figure out the corresponding z values for a standard normal model. What two values of z have the property that the center portion is 80%? And then what we're going to do is we're going to take those two z values and convert it into a corresponding test value. All right, now, so if I want this center portion here to be 80%, what will be the two wings? Now, I haven't drawn a particularly good diagram. Let me just change this a little bit here so it looks like it's symmetric. What can you tell me about the sums of areas to the left and right, the unshaded portion? How much is that, both of those together? 20%. What that means is this right here is going to be 10%. This is 80%, this is 10%. Now what I can do here is the following. I can find this value here by looking for the entry closest to 10%. This value here will be the value associated with 90%. These two values will be the same except for their sign. One will be a positive number and the other one will be the negative. This will be the positive value, that will be the negative value. That has to do basically with the symmetry of this normal model. So what is the value associated with 10%? Well, if we look in our table, let's see, that's going to be okay, these are the two entries which are as close, or the closest to 0.10. This is a little bit above, that's a little bit below. So this entry here is a little closer, so I'll use that. The z value will be a negative 1.2. And then if I go to the top, that's going to be, at the top, it will be 0.08. So I want a negative 1.28. Now I could look for the entry in the table where this is associated with 90%. If this is 80 and that's 10, then the total area to the left would be 90. So I look for an entry associated with 90, but it's simply going to be a positive 1.28. Okay, so now, how do I figure out these two values? Well, I convert both of these back into x values. So the first x value will be 100 plus a negative 1.28 times 16. And then the next value will be 100 plus 1.28 times 16. The 1.28 is the z value. All right, and this will be .79.52, and that's approximately equal to 80. And this is going to be 20.48, which is approximately equal to 120. So the center, 80% of scores will lie between 80 and 120 approximately.
So, when you're writing out your answer, do you write it out in a sentence like that, or you just?
Well, I would.
Or can you just?
It's acceptable to. I mean, for example, in 40C, I would accept I mean, if you tell me between 80 and 120, I kind of cringe because I want to say, how did you get those? Did you look in the back of the book, or did you look in my notes and copied it down? I like to see some evidence, some thought was involved other than copying, okay? But you don't necessarily need to write down a sentence. I like people that do a numerical sketch or numerical calculations.
So if we just have these two equations that you just did, that could be our answer.
Yeah, I mean, yeah, I would, yeah, I think, you could have both of these here, and that tells me you pretty much have understood the problem.
Okay.
That's what I want. And of course, that's how I'm going to test you on the exam. Sorry, that's the way it works. Yes? I don't hear you. Well, units, you see these, it's just a score on an exam. I don't really, that's a good question, I don't know. It's not feet, it's not inches,
like math people.
Right?
We're all thinking like math people. Like, how do you write the answer?
Yeah.
What's the units? Right?
Oh, okay.
Another class.
Yeah. Who, why don't you give one to the, and you can put it on the computer if you want to use Excel. Hide your monitors if you're going to stay here.
Okay.
Because these people have yet to enjoy the experience.
Right. Okay.
That will come shortly. Okay. I'm not quite sure. The question says, I want two values, symmetric about 100, where this area is 80%. So I'm looking for two exam scores. The distance above 100 and the distance below should be the same, so that this is 80%. That's what it means when it says the middle, 80%. They're talking about the symmetric middle. What I do is I ask the corresponding question for the standard normal model. What z values have the property that between symmetric values about 0, symmetric values about 0, one is going to be positive and the other one is going to be the negation of that. Where is this 80%? Well, if this is 80%, this plus that must be 20%. This must be 10%. So I can look up in the table to see what is the value associated with 10%. It's a negative 1.28. The corresponding value on the other side must be 1.28. So these two values then are converted back into the corresponding values for x. Notice that 80 is 20 units below 100, and 120 is 20 above. So it's symmetric about the center of 100. It would be from 80 to 120. So the center, or the middle, 80% is from 80 to 120. Okay. All right, let's see. Mu and sigma are known as parameters. This is the bell-shaped curve. I've used the standard normal table. The standard normal table gives us, we can either think in terms of areas or percentages, okay? This little diagram is what I've been using. This here is intended to represent some normal model. You can kind of ignore this capital X tilde for the moment. This bell-shaped curve is centered at mu and then has a standard deviation of sigma. Any normal model has an equivalency with the standard normal model, that is where z or n is, or mu is equal to 0 and sigma is equal to 1. If you give me a value along here, I can use this equation here to find the value of z along here. Or if you give me a value of z along here, I can use this formula to find the corresponding value of x. This is what I've been doing. I've been translating back and forth. Okay, now, when I compute, I've been using this formula right here. This is known as computing the z-score. There may be circumstances where I want to compute a z-value associated with real data. In real data, I don't know what mu and sigma are. What I can do instead is use estimates of those values, the sample mean and the sample standard deviation, and I end up with what we call z-values. So z-values can mean a theoretical value, which is this equation here, or it can be represent a value associated with real data. Okay, it's the context that determines which one we're talking about. We're going to ignore this one here for the moment. These are two examples of, three examples I gave of normal models. But they're an infinite number. There's no limit. The one that we've kind of constantly referred to would be the standard normal model, where mu is equal to 0 and sigma is equal to 1. That's the blue curve here. Okay, now, let's see. What I'm going to do is the following. I'm going to go through this. We'll spend about 5 minutes on that, and then we'll take a break, and then we'll do the quiz after that. Okay? I haven't gotten as far as I wanted to, but it's close enough. All right. Sometimes we have data in one set of measurements, but we'd really like to convert it into a different set. For example, you might have recorded temperatures in Fahrenheit, and you want to convert that into Celsius. Or you might have data in terms of Celsius, and you want to convert it into Fahrenheit. All right, now there are two formulas that you probably have had before in math, and those formulas are as follows. I need one of those kind of neck things with an elastic thing so I don't lose these. All right, so the formulas are Fahrenheit is equal to 9/5 times Celsius plus 32, or Celsius is equal to 5/9 times the Fahrenheit minus 160 over 9. You've probably seen those before, and you may have seen these values in their decimal equivalent. All right, we don't need that. If I have temperature in Celsius, this can be used to convert it to Fahrenheit. If I have temperature in Fahrenheit, this will convert it into Celsius. Both of these equations are equivalent. Once I give you one, you can solve for the other. They're both known as linear equations, or sometimes called linear transformations. Now, when I have data that is transformed, there are some ideas that we can make use of, and that is as follows. This can be referred to as scaling or linear scaling. In this diagram up here, I have an equation where on the left I have the letter X with a subscript of new, and on the right I have the letter A, the letter B, and the letter X with a subscript of original. In this equation, I'm assuming that I have certain constants A and B, all right, and that this symbol right here represents a measurement in my original units. So if I measure temperature in terms of Fahrenheit, this would be one of those values. I can, in fact, convert that into Celsius, all right, and the X with the subscript of new represents the same temperature, but using the Celsius scale. This equation right here actually is of this form. This coefficient 5/9 would be the B, and the negative 160 over 9 would be my value of A. So this here fits this pattern, and this fits that pattern as well. There are different values of A and B. The point is, sometimes I want to convert from one format to another, or one transform to another. There are certain, if you will, rules or theorems that apply when we do these linear transformations. Here, in this first equation right here, you see the same letters A and B as I have up here, and I have an X bar with the subscript original. This says, if I want to know what the mean value, the sample mean value, would be for the new units, all I have to do is know what my A and B are, and I take A plus B times the mean in the original units, and that will give me the mean in the new units. Same thing holds for the median. Again, assuming that you know what A and B are, I mean, that's typical if we're going to do transformation, we know what those values are. If you tell me what the median is in the original, for the original data, I can plug that value in here. I use the values of A and B, and that resulting computation will be the median of the values in the new format, or the new units. For the standard deviation, if I take the original standard deviation and I multiply it times the absolute value of B, B could be negative. I need its absolute value. If I take the absolute value of B times the standard deviation of the original data, that will be the standard deviation of the data in the new units. The interquartile range of the new units would be B times the interquartile range of the original units. The range, the new range, which is the difference between the maximum and the minimum, would be the absolute value of B times the range in the original units. Now you could actually convert your values, say from Fahrenheit to Celsius, and redo the calculations. But these rules always hold. These are actually theorems in math, and we could show them. I'm simply going to state them. Now, sometimes it is useful to have other transformations other than linear transformations. We're not going to go into this because it's a little too involved. Sometimes you have data that is better understood if you look not at the values themselves, but if you look at the logarithms of the values. You may remember in your college algebra classes, you were hoping never to come across logarithms ever again. Regrettably, you just have. Sometimes it makes sense to take the logarithms of your values and work with those instead of the original values. These rules don't apply in that case, but that's sometimes useful to do. All right? And there are other sorts of transformations as well. And if you get really deep into this stuff, you can you'll find out more stuff or more details. But I want you to be aware of the fact sometimes our regional data is in a format that's not the best format, and we may want to have a transformation. If it's a linear transformation of this form, which an example of which would be conversion from Celsius to Fahrenheit or Fahrenheit to Celsius. If we have a linear transformation, these rules hold. On the other hand, however, if we're using logarithms, that doesn't hold. Okay, now a preview of what's coming ahead is the following. This is some data that I acquired in 2009. It was apparently there was a real estate agent who had apparently a lot of time on his hands in 2009. We know why this was the case. That was when the economy was in free fall and everyone was screaming. These were actually houses that were sold in 2009, in the fall of 2009. Okay, and it's a little surprising to me today to think, were they actually selling houses in 2009? Apparently they must have been, but it must have been. I suspect these were probably cash transactions or maybe foreclosures. I'm not quite sure. Okay, so someone had a house with 1,484 square feet. It was built in 1998. It had 2 bedrooms. This is their notation for 2.5 baths, and it had a selling price of $250,000. It was on the market, days on the market of 101 days. There was another home having 1,663 square feet, 3 bedrooms, 2.5 baths, built in 1987, also sold for $250,000. Okay. Now, what I've created over here is what's called the scatter plot. Basically, I've plotted along the horizontal the number of square feet, and along the vertical is the sale price. That's represented by all these little dots. Now, this is what we call a scatter plot, and Excel does things like this very nicely. There is something called a linear regression line, which I have determined right here. I'll show you next week how you do this. Basically, this line right here is described by this equation, and basically it says, you tell me what the number of square feet in a house is. I'll stick it into here, and I'll give you an estimate of what the price of that house will be. This value down here, which is r squared, make that a little bit bigger. R squared here is about 0.59, or we would round that up and say 60% roughly. Basically, it says this line goes through the data fairly nicely. You can see some scatter about the line. We use linear regression all the time. Everyone in economics, I mean, this is their bread and butter, basically, in economics. They'll use either linear regression or multiple linear regression. It's a way of creating a relationship between 2 variables. Okay. So this is what's coming up in Chapter 7. We'll start this next week. I now have, by my watch, about 25 of. You can take a break. When you come back, I'll give you a quiz. You take the quiz, and when you're done with the quiz, you can take off. Is that good enough for now?